Hi everyone, my name is Pranjal and I'm an AI scientist working for Polymerise. I'll give a quick introduction to myself. But let me first introduce what we're going to be talking about today, which is how to stack neural networks together. Right? So for everyone who's been into ML or AI, we've developed a lot of neural networks. We worked with CNNs, DNNs, new age technologies like graph neural networks and stuff like that. But there is an application of neural networks that really helps build a lot of more ideas into the field, and that also helps us to combine powers of different kinds of data sets into one. Right? So I work as a data scientist, AI scientist, machine learning engineer at Polymerise. It's a material science company based out of Singapore. We are developing the next generation AI platform to fuel the growth of R&D scientists across the world. I'm a big Python fan. I've previously worked in a marketing AI platform, developed it from scratch, where we increased the ROIs by 1.5, 1.6x for all our clients across the world. I have been corely involved in explainable AI. So explainable AI is something that I'm really passionate about because I really feel opening up the black boxes are going to help us understand the data and not just predict with a higher accuracy, which sometimes is misleading. I've also focused my areas of research into tabular neural networks because neural networks in terms of CNN, they have a lot of data, there's a lot of content available online, and it's a lot like copy-paste. But when it comes to deep neural networks from tabular data, it becomes very essential because that has a lot of applications in the industry which might be missing. Right? Reinforcement learning, I've done quite some work on reinforcement learning for the supply chain domain to optimize for costs, times of delivery, et cetera, et cetera. And largely, my current focus is fully on optimization. I'm going to be giving you guys a bonus optimization idea that I think will be really helpful for all of you who've been building models. And finally, MLOps is where I try to make sure I learn every day, because until and unless you can put your models in production, those models are practically invaluable. Right? Let's move forward. So what is stacking? When we talk about stacking of models, what we are trying to understand is we are trying to get multiple models together and use their individual specific powers as one. Right? How does it help? It helps by decreasing your error variance. Right? Suppose there's one model that performs really well on a certain kind of data set, and there's another model that performs really well on a certain kind of data set. You can consider an example of outlier-based data. For example, we know random forest works really well with outlier-based data sets, but it does not, linear regression does not, right? But linear regression works really well when the relationship between data is linear, but random forest may not. So in cases where those situations can occur within the data, we can actually use the capabilities of both the models to get a higher accuracy or at least a comparable accuracy with the best individual model you have, whilst reducing the error variance to a minimum. We'll be seeing an example of that soon. The second thing is it has to be differentiated from bagging and boosting based models. Right? When we talk about bagging a model like random forest, so every individual model which is a part of the random forest is a tree. But when we talk about boosting models, then every next level model is dependent historically on the previous model. Right? So how does stacking fundamentally differentiate itself from bagging as well as boosting models? When we talk about stacking, it is different because there are multiple independent models. So these models have no impact within each other. That separates it from boosting, which you can see. And the second one is where they are all heterogeneous. They can be different models, which separates itself from bagging. So random forest has multiple trees, but a stacking model can have different fundamental models, linear, Bayesian, decision trees, et cetera, et cetera. Right? Now, coming to the conclusion of why do we want to stack neural networks together, okay? Let me give you an example. Suppose, we're going to be covering that in a lot more detail today, but let's imagine a situation we want to predict the price of a house. Now, I know all of you will be, again, the same data, again, the same model. We can go online and just fetch everything ourselves, right? But imagine a situation where you have not just the features of the house, but you're also having the images of the house, which is easily fetchable, right? When we're collecting data, we can collect images, right? Taking it a step further, we can also collect images about individual parts of the house, right? We'll see an example where we have the frontal view, the kitchen, the bedroom, and the bathroom, right? Essentially, what we can figure out are details from images that we might not be directly getting from features. For example, is there a crack in the ceiling? Right? Can you get that anyway from any features which is not an image? It's very tough. Right? I mean, even if there is, the data can be inaccurate, the data can be incomplete for a lot of houses, and you know how data is. So we must ensure that we have the capability of incorporating different data sets from different sources if need be, and then compiling them together and adding them to a neural network. That's what we are going to do with stacking. So what kind of data sets do we have? We can have images, we can have text data, we can have tabular data, we can in fact have voice data, and we can combine the powers of all of them with the individual networks we know, right? How does it help? It enhances the capability by incorporating multiple informative sources. Like we said, each model can be fine-tuned separately, or as well as they can be fine-tuned together, right? You can combine and hypertune, or you can individually hypertune and then combine. Those kind of functionalities, very easy with TensorFlow. We'll be seeing that in the example. Now, each of these models can individually handle different data sets, right? Let's take, for example, that you have a categorical data set and you have a numerical data set. What we do is we combine the entire data and build a single model or a deep neural network with them. But what happens there is the categorical data needs to be labeled or binarized, and then it gets passed. So the size of the network increases in the first layer, and it has to be eventually passed on to the eventual layers of the model itself. But what if we could make a separate neural network for numerical data and a separate neural network for categorical data, and then those two models can be stacked together to make a prediction? It will actually help us reverse engineer the importance of the features with explainable AI. Otherwise, explainable AI and a lot of these algorithms that we've heard of, let's say integrated gradients or deep lift or SHAP, all the popular algorithms that help in explainable AI, they are sometimes not very well working with the sparsity or high sparsity in the data set. So we can separate them and individually explain the values. That makes a lot of sense. And also, we can finally use that for transfer learning. So you have VGG16, DenseNet, ResNet, all the popular models trained on the ImageNet data set with a great deal of better performances. We can just make their last layer removed, and we can also set them to not be trained and just use them as a dimensionality reduction technique to get the best features out of our images by using the top-end models that researchers and developers have built, right? An example that you see, the image here, is of the different models. You can see linear regression, you can see KNN, you can see CART, you can see SVM, Bayes, and stacking. What you'll notice here is stacking might not be always the best performing model, but it will always have a less error variance. As you can see, the size is always lesser, so you are more likely to not have a very randomly or abruptly performing model. These models will be robust to the situation. So in a high pressure situation, in a very risky situation where models have to be built, you can use stacking to make sure the error variance is low. Right? Any questions so far? Yeah? Okay. So on the y-axis, you have the error, right? The errors are basically plotted in a box plot. The box plot center is the mean, then there's the quartile 3, quartile 1, right? Interquartile range, minus 1.5 times that one. So if you see CART as the model, or let's consider linear regression, right? So the error, if you see 0.8 to 0.94 something, so there the size of the error is very high. They can be very low, yeah? These are different models. Okay, so this one is linear regression on the absolute left, LR, then there's KNN, then there's CART, there's support vector machine, there's Bayesian regression, there's stacking. Okay, any other questions? Okay. Right, so what are we going to be building today in this tutorial? We're going to first give a quick example of stacking classical ML models. This will be a quick, I'll be showing the code, I'll be looking at the results, and we'll be sharing if there are any thoughts. The next what we are going to do is we're going to stack two deep neural nets together, and we are going to be talking about the fundamental decisions that we are supposed to make. For example, do we train the last layer? Do we have multiple final layers? What should be the sizes, right? And all the other critical details will come up. And finally, we are going to be training a stacking DNN, which will have a numerical network, a categorical network, and 4 CNNs stacked together. I know the image might not be very clear, but it's a pretty complicated network to work with, but it'll make sense when it comes up. Right? So the stacking classical ML model will work just like this model that you see here. There'll be an input. A copy of that input will be passed to each of the 3 base models, which is the first layer. And the output of the base models will be learned by a final meta model. It will also be trained in the process, and you will have the final output. Right? We're going to be use Scikit-Learn, obviously, with the Ensemble module, and we get stacking regressor and stacking classifier. It's pretty easy. We'll just quickly see in a minute. Okay, so let's head over to the code. I hope everyone's able to get the tutorial Slack link so you can open my GitHub profile, and we can go to the first notebook which says classical ML stacking. I also learned something interesting from github.com. You can just do GitHub and then try toColab, and it automatically switches into a Google Colab sheet. Right, I'll be connecting. Yeah, sure. Sorry, 1 second. Oh, it doesn't work that way. github.com/datagasmic. Yeah, sorry, there was a question.
Yeah, if you go to that track to Colab, does it then automatically take care of the dependencies?
No, we'll have to install them, but most of them are already there with Google Colab, so we don't have to work. There's going to be one library that we're going to use in hyperparameter tuning stack networks. There, we'll need to install a library specifically at the runtime. Okay. So we import the basic libraries for ML. Anyone who's ever built a machine learning model, they definitely know. Pandas, NumPy, train test split, linear regression, k-neighbors regressor, decision tree regressor, support vector regressor, and from the Scikit-Learn ensemble, we get stacking regressor. And from the metrics, we quickly pick a mean squared error, right? The metric can be of your choice. What's important is how it is related to the other models individually and as a stack. Right, I'm going to be picking the California housing data set because it's available with Scikit-Learn. It's going to be pretty quick. Sorry? Yeah. After GitHub, you have to type toColab. github.tocolab.com. Not .tocolab, github.tocolab.com. Okay, we have our input and output separated with housing data, housing target. And we also do a train test split. Now comes the first section, which is the individual models, right? Here, the process we're going to be following is we're going to train individual models, observe their performances, observe their error variances, which you can see printed on my screen. I'll just quickly run the cells and make sure everything's working fine. So there's 3 initial models that I took: support vector regressor, k-neighbors regressor, and decision tree regressor. I quickly ran a loop to fit it on the training data and predict it on the test data. And there's a small print statement that prints root mean square error and the error variance with np.var. Just quickly scroll my screen to the right so you can see. Right, let me run this cell. I joined the conference last minute, so please pardon that I did not put it in a data frame so it can be represented nicely. I just made a print statement as soon as I could. It's because of the support vector regressor that it might take some more time. Support vector regressors are nasty in terms of taking more time. Okay. So right now, the best performing model is decision tree regressor with 0.72 root mean square error. And it also has the minimum variance of 0.309, right? Now, a requirement of the stacking regressor from Scikit-Learn Ensemble is that you need to have a list of tuples where the first element of the tuple is the name of the model, so it's uniquely identified, and the second is the actual model. So I've just done name of the model, comma I for individual models. So that will give me a list of tuples where each element in the tuple would be the name of the model and the model itself. And then the second part, which is the meta model, which is the model that's going to be taking output from individual models and then be learning from the next steps, right? And finally, we have the stacking regressor. So you can see stacking regressor has estimators, which is the base layer, final estimators, which is the meta model, and CV equals 3 is integrated in Scikit-Learn, so it's a cross-validation. Yeah?
Is it possible to use Dask stacking data sound?
Sorry, please repeat your question.
Yeah, is it possible to use Dask for that?
I am not sure, but there'll definitely be an opportunity. It has n jobs equals -1, so it's doing distributed training for sure. We can use Dask as well, I think. Yeah. Yes, one very important question here that we need to address is pass-through equals false, right? Pass-through equals false is very important because it tells you if at the time of training this model, are you going to be training all of them together or are you going to be training them individually? So if you said pass-through equals true, it's going to take the input data and it's going to train all the individual models together, right? But if pass-through is false, then the individual models that will be trained will remain the same and you are only going to be training the meta model individually, right? So it is going to combine the outputs of the base models. Let's say it's a linear regression equation, AX1 plus BX2 plus CX3. So it's going to be learning A, B, and C for X1, X2, and X3 in different data sets, right? N jobs -1 is for distributed model training. And we run it. Simple fit, X train, Y train. Predict, looking at the mean square error, and looking at the variance, yeah. I would set pass-through to true in cases where I do not want the meta model to be very biased. What happens is sometimes, let's say a decision tree regressor model is working really well. So if I have the meta model with a pass-through equals false, then it will largely be taking the decision tree model, right? But if I have comparative models, I would rather do pass-through equals false. But if I have non-comparative models, let's say the data has a drift, in those cases, I will be doing pass-through equals true. So it knows for every instance which model performs really well. Okay, so we have the best performance in terms of lowest error, 0.67. If you go and compare, it was 0.72 here for decision tree, as well as the error variance, which was earlier 0.309, which was the minimum. We now have an error variance of 0.23. I hope this slide and the code is clear. If there are any questions, happy to take them. Yeah?
To make sure I understood what you've done, if you actually save the output of both models and actual, you could have trained that regressor, right?
Yeah?
You could have done the same regression with the output of the other two models and then train it and
Yeah.
have the same results, right?
Yeah.
Because you're setting pass on false.
Yes. Okay, so this is done. Now, let's talk about the fundamental questions, ideas, and decisions that we need to take when we stack a neural network, okay? So the first question, data-based model selection. Do you want different models of different designs, or do you want different models of different types? Let's say you want a deep neural network and a convolutional neural network, or do you want two deep neural networks to work simultaneously, right? A lot of times what we've done at Polymerize is we've created a very long network, and we've also created a very tall network in terms of their designs. And we've tried to understand in a lot of cases where the width sometimes performs better and sometimes the length performs better. So the bias in the data, let's say you have some kind of outliers in a particular set of variables in some data set. So a larger model works really better with outliers, but with non-outliers, the taller model works. So we've sometimes combined two different design systems in a neural network and have made it work. The second question we need to ask is, do we have different data sources, right? First of all, can you collect different data sources? That's obviously a question we need to answer first. But if you are able to collect different data sources, how do you stack them, right? I'll give you an example of graph neural network that will make it a lot clearer, because sometimes the networks need an embedding layer. The sizes of data are different. Just giving an example. Let's say for my domain in material sciences, let's say you have 5 ingredients in a formulation, in a chemical reaction, and in another experiment you have just 4, right? So if you collect the structural property relationship of each of these ingredients, at one iteration you have 5 structure property relationships, and in another iteration you have just 4, right? So in cases like those, we create embedding layers just to make sure that the final layer sizes match with the next steps, right? The second question is the training process. Do you want to train the networks individually first, tune them to their best capabilities, and then stack them? Or do you want the models to learn together, combined, right? And obviously there's the third case where certain models are individually trained and certain models are trained in a combined way. Let's say the DNN and the CNN can be trained together, and we can also use a pre-trained model on the image data set, right? So that decision is also something we consider. The final layer. Do you want the final layer to be directly coming from the stacked networks, or do you want an additional dense layer before the output layer and the stacked networks, right? For example, if you have a huge stack, right, you cannot directly have a single output for all the 20 or 30 or 40 nodes that you will have in your stacked output. So we'll also need a dense layer to be connected with the stacked output and then have the final node that makes a prediction. We'll see that in the tutorial example. Hyperparameter tuning, again, very important. Do we hyperparameter tune the entire stacked model, or do we hyperparameter tune only singularly and then combine? And finally, pre-trained models. Do you want to train pre-trained models? Let's say you can just set trainable equals to false for any pre-trained model you have, or you can also train just the last layer. You can individually, selectively deny the training of certain layers of the pre-trained model. That's also possible with TensorFlow layers. Okay, so we're going to be building this, okay? The first network has its set of properties and characteristics. The second network has its own set of properties and dimensions. And then we have this final layer, which you can see as the concatenated layer, right? The concatenate layer is where we're going to be focusing and trying to find out how to build that entire section, how to connect them together. And then we have the final dense layer, which is going to be the prediction output layer. Okay, so we build network 1, we build network 2, then using the keras layers.concatenate, we concatenate the output of the 2 networks, and then we finally create a dense layer, which is going to be using the functional API of TensorFlow. We are going to be combining the input of the 2 individual layers, okay? And another key aspect of this is we need to also apply the same dimensions while predicting, which we are while building the model. For example, the input of the first network and the input of the second network, they can be the same, they can be separate. So while making a prediction, we'll have to ensure we pass to TensorFlow the input that goes to the first model and the input that goes to the second model, right? Any questions, or we'll move to the code? Okay. Right, so I've just imported all the essential libraries that I'm going to be needing throughout. Quickly running this. Fetching the California housing dataset. Now this dataset has 2 additional parameters, latitude and longitude. A lot of times, latitude and longitude are used to derive certain kind of properties. For example, mobility can be derived by using the latitude and longitude. And there was a company presenting earlier, Mobile Wallah team, they do this with your latitude and longitude. They actually give you the mobility statistics. So you can actually convert latitude and longitude to get the mobility, or you can use them in terms of numerical data with respect to how far, how left or how right it is, how top or how bottom it is. So we'll look at that. If you do not want to train on latitude and longitude, just attaching this indexing would work. Okay, in the train test split, please observe that I've added a random state. Okay, random state is for repeatability of results, definitely, but when we are stacking 2 neural networks, we have to make sure that the training data goes, the same training data goes to both the networks at the same time. Otherwise, the output would be something else. And one network would be trained on some data, the other will be trained on some data, so they'll never be able to reach the target. Right, so random state, important. Right, building the first network, again, simply building a neural network, sequential, adding one dense layer. Sorry, there's the question? Okay. So adding 4 dense layers, the final one is the 4 units layer. Now observe closely that I did not make a final prediction on this. I did not make the final layer to be 1. And also, I did not compile the model. I did not compile the model because this is not where the network 1 compiles. The network 1's output is going to go to the stacked model, and it's going to be compiled in the final stacked model. So we are not going to compile the network 1. We're just going to create the network 1. Right? We'll quickly check out the summary. Right? Nothing new, nothing strange, nothing fancy. Network 2, I've changed the dimensions a little bit. So now there are just 2 hidden layers with 16 nodes each. And again, I do not compile the network 2. Now this is the crucial step. This is where we start stacking. Okay? Combined input is equal to the concatenation layer from TensorFlow. Right? This is where the real game is happening. Network 1.output and network 2.output. Right? So the list has 2 elements. 2 models are getting stacked, network 1 output, network 2 output. And the combined input layer, which is the concatenated layer, it gets passed on via the TensorFlow functional API to the next dense layer, which has final node 1, activation linear, right? And this is where we have compiled the 2 networks with a final dense layer, which is going to give us the output. And finally, we are also going to be using the module, where the inputs will be network 1.input, network 2.input, and the outputs will be X, right? Now, just looking at this, I think it makes sense that no matter what model we have, everything is just now another comma-separated value in both the lists in the concatenated layer and in the model submodule. Right? You can add as many modules as you want. You can add as many models as you want, and you can concatenate as much as you want, and then you can just use the final model building API to get the inputs and the output. Right? Once you're done executing this, I'm sorry, I did not run the cell above. Once we're done with this, quickly check the model summary. Right? You see there's a concatenation layer here. Right? Sorry? Same input layer? Yes. We're going to be passing the same input data to all of them. So the input layer does not get transported to both the networks. The input layers for both of them are separate, but the data is going to be the same. Okay, so this is my network. One of them starts here. They get concatenated here. And I have the dense layer, which has 1 node in the output. Right? I'm going to be using Adam and compile this stacked model. Then I'm going to fit it. When fitting, the X has to be passed. The X trained data has to be passed multiple times because the 2 models are going to be taking as input. You can actually relate this to this. Right? The inputs coming for the model will be coming from both X trains. And we take certain set of epochs and batch size. Pardon me, I am not going to be training this for a lot of epochs and showing you the results because that's not relevant for the talk. But I just want to show that it works and the error is significantly reducing. And while making a prediction, again, I have to pass X test in a list for both the networks to work. Finally, we can check the performance. Also, an interesting fact is that I can access the network 1, network 2, and the models separately. Now, why is this essential? let's say I want to understand and explain the network 1 individually, right? Let's say network 1 is a convolutional neural network, right? So I would like to observe the important parts of the picture of the image separately, and I would want to know the importance of numerical features that my deep neural network is trained on separately, right? So because I can access individual networks from this tagged layer, I will also be able to explain them either layer-wise or node-wise towards the output and how they contribute to the entire model. Okay, it will also give us a sense, let's say you want to decide if you want to buy the image data of the house. A lot of people, a lot of companies are buying data sets from these big data management platforms, right? This is an entirely new area. So you can also negotiate on the quality of data that you're getting. So let's say in making a prediction, 30 to 40% of importance is coming from a particular vendor who's providing the image, right? And from another vendor, you're getting 50 to 60% importance of the final prediction. So I would choose which vendor to when I'm doing the explanation, right? So that was the fundamental idea, the concatenate layer, the functional API, as well as the final model that I can build with TensorFlow layers. Coming back to the slides. Now let's look at a really, yeah, sorry? Okay, so what I was saying is, let's say you have a convolutional neural network, which is going to predict using the images, and you have a deep neural network, which is going to predict using the numerical features that you've got, right? In that situation, how much of the prediction is getting impacted by the image data, and how much of the prediction is coming from the numerical data, to understand if images are more valuable or the numerical data is more valuable. For example, if you take a house, number of bedrooms, number of bathrooms, the example that you can see, area of the house, these three features, they'll be common across a lot of houses, right? But the image is going to separate the quality of the house when you compare with bedrooms or area, et cetera, et cetera. The zip code, obviously, it is a categorical feature. So zip code will be dealt separately. We're going to be building a categorical neural network for the same. And finally, the price is the target column. I hope that makes sense. I don't think we'll have time for that, but I'd sometime love to talk about the explainability part of it. I have spent around 6 months doing that, yeah.
Is there the assumption here that for each input data type, we have, like, basically we have for each target, we have all inputs of the different sources, or
yeah.
what they're missing?
If they're missing, we'll not be able to deal with that. We'll have to ensure that all the data is available when we're making a prediction. So for one house, you're going to need the 4 images, and you're going to need the data row as well. If one of them is missing, it might be a problem, but we might default, we might set some default for some missing values. We can take averages and fill the missing values, just to make sure that the other parts of the house for example, let's say a house does not have a pool, right? A swimming pool. Let's say we have swimming pool images, a house does not have a swimming pool. Right? In those cases, we'll have to find ways to manage them. We can actually have empty images as well. We can just concatenate white images. That's fine. Okay, so we're going to be talking about this example. The link to the research paper where I found the data set is there. The link to the GitHub where I found the data set is also there. It's an amazing paper. I would want everyone to give it a read whenever you get time. But practically, this is the data set in front of you. Right? In the houses data set that we're going to be cloning from GitHub, we have for every house 4 images. We have a bathroom image, a bedroom image, a frontal view image, and a kitchen image. Right? And this is for all the 535 images that we have. And for each of the houses, we have their numerical features, which is number of bedrooms, number of bathrooms, area of the house, zip code, and its price. Right? So what we are going to be doing is we are going to be building a separate network for the numerical data, a separate network for the categorical data, which is obviously the zip code, and we are going to be building an individual convolutional neural networks for the 4 sections of the house, images for which we already have. Right? So let's move to the code. We are going to be building this First, we're going to prepare the data. Obviously, the data is not available exactly the way we want, so we're going to have to work with it. Neural network with numerical data, categorical data. We have to binarize the categorical data. Convolutional neural networks, concatenate all of them together, add a dense layer, post concatenation. So this is why I was saying that an important decision in stacking is, are you going to add a layer between the final output layer and the concatenated layer? A lot of times when there is a lot of stacking, we need to ensure that there's another layer that knows the importances of individual models. But if there are simple stacks, 2 or 3 neural networks which are mostly similar, getting past the same data, then you can directly have them in the final output layer. And this is what we're going to be building. Let's quickly see that in code. Okay, any questions so far? Okay, cool. Great. I have all the dependencies I want. Pandas, NumPy, CV2 is for images, IO is for imread, which is to read the images into NumPy arrays. Glob is for accessing the files that I'm going to be cloning into my drive. Label binarizer is for helping with the categorical data. Train test split. For the model, I have TensorFlow sequential model, flattening it, dense, batch normalization, conv2D, max pooling, activation, dropout, so on and so forth. I also have the layers and models, Adam, plot model. Okay. Now, this is the step which will help us get the data set. Let's quickly run this. It's going to download data set. For me, it's there because it's just reconnected my kernel. And here is the data set. The folder is large, so you might have to double click on this, and you see this. So you have 4 images of the house 100, 4 images of the house 101, and so on and so forth for all the 535 houses that we have. They also have a houses info.txt file inside this folder, the houses data set, which will give you access to bedrooms, bathrooms, area, zip code, and price. To sort them in order, I had to write this small piece of code which takes the root path and generates them in order, because if you sort, Python has that 0, 1, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So after 1 comes 1, 0, and not 2. So to help with that, I had to create this small amount of code. It's going to get bathrooms as a list, all the file names in order, 1, 2, 3 till 535. And it's going to do the same for bedrooms, kitchens, and frontals. Right? This is the name of the text file. You'll find it in the folder. The columns were not mentioned directly, so I had to write them from the documentation I read. And this is my data frame. I do a quick check, by the way, for the question you were asking. I do a quick check for any is nulls and the shape of the bathrooms, kitchens, bedrooms, and frontals, just to make sure that I don't have anything missing, because that will not let the code work the way it should. Okay, so I have the 3 columns for numerical columns, which is bedrooms, right? Bathrooms and area, which are these first 3 columns, right? I have zip code for the categorical columns here. Now following the steps we discussed in the slide. The first is the numerical DNN, starting with sequential, adding a dense layer, input dimensions coming from the numerical columns of the data frame, the ending units to be 8, hidden layer. Then dense units 8 again, and finally it is going to return 2 nodes in the final layer of the first network. Processing the categorical data, initializing the label binarizer, doing the dot fit transform on the categorical data. It's going to completely burst open the data set for zip codes. Number of unique zip codes will become the number of columns after binarizing these labels. I hope there's no confusion with that. Let's run this cell as well. Categorical DNN created. Again, not a lot of effort put into number of nodes or number of layers. It's just for the sake of explanation of how to stack. We can definitely try and hyperparameter tune them. I'll give you an example with RayTune, one of the distributed hyperparameter tuning frameworks. Yeah?
But if you were to train all the models in parallel, or like the stack model altogether, so how would you go about hyperparameter optimization? Because you would have all the individual hyperparameters of the different models, plus from the stack one, so the grid search would be huge.
Yeah, that's why we're not going to do a grid search. We're going to do Bayesian optimization with hyperopt and RayTune, which is a distributed framework. It can use GPUs, and you can initialize as many model trainings together. I mean, the number of processors you have is equal to the number of models you can train at a time. We'll see an example. The notebook hyperparameter tuning stacked regressors, it has all the code, and yes, you're correct, the hyperparameter space is going to be huge, but I have the added advantage of hyperparameter tuning each aspect of each of the models. So I can use different kernel initializers for different models. For categorical data, the kernel initializer might be different. For numerical data, the kernel initializer might be different. So we have the ability, we'll be just coming to that in a minute. Okay, so categorical DNN created. Now each of the data sets from bathrooms, bedrooms, kitchens, as well as frontals, they've been converted. The images have been resized to a common shape, and the NumPy arrays have been concatenated to individual lists, converting all of them into arrays to be directly used. Y is obviously the price column, which is fairly simple, right? Now, coming to this segment again, lots of code, but mostly copy, paste, and edit. I, again, apologize for such nasty code in front of all the Pythonistas here, but again, last minute, apologize. Bath train images, bath test images, Y train and Y test, again with train test split, bathrooms data Y, train size set to 0.8, and please do not forget random state 42 for all of them. Otherwise, you'll be using different data sets and different outputs for all the models, which will not make sense. Now you have the same for the bed, same for the kitchen, same for the front, right? And the last two lines are for numerical and categorical. Okay, so I have the training data set matched in order for all the 6 models that I'm going to be training, and I'm going to be using the same test for them. Any questions? Okay, image data sets need to be processed. They need to be scaled with 255 just to have values between 0 and 1, so that's just it. Okay, because I had to create 4 convolutional neural networks, I did something simple. I created a function that will return a convolutional neural network, and I can just directly create 4 CNNs. I have a convolutional layer, max pooling, again a convolutional, max pooling, again finally a convolution and a flattened layer. Finally, the dense layer, which is going to give me the output of the network. And I create 4 CNNs. Now, back to square one. Concatenate numerical DNN.output, categorical DNN.output, bathroom model.output, bedroom model.output, kitchen, and frontal, right? So I combined the output of all the individual neural networks I have into one layer, which is the concatenation layer. Post the concatenation layer, I will now have a dense layer which has 6 nodes. This is what we were talking about earlier. When you want to add another layer between the concatenation layer and the final output, this is where we do it. Again, using the functional API, the combined output gets passed to the dense layer that we create. And the final layer has, again, a dense layer with 1 node. And functional API gets X into the final layer. Finally, I'm using the model in TensorFlow. The inputs are defined just like I defined the concatenation layer. And the outputs is my final layer, which I just created here. Right? I run this. My neural network is ready. My stacked neural network is ready. Optimization with Adam and model compile and plot model. Looks very complicated, but we all know what we did. We have 4 CNNs, 1 numerical DNN, 1 categorical DNN. Okay? Now, fitting the model, again, the only thing that changes is the input to the model, because the input will be, again, in the same order, numerical, categorical, and all the 4 images. Y will obviously be Y train. I'm running it for a small number of epochs and a small batch size, just to prove that it works seamlessly without any kind of issues, and the error decreases at every epoch. Okay, we can skip that. Prediction, again, model.predict. The input that goes into the prediction is going to be the test of the numerical data, the categorical data, and the image data together, right? And then we can simply do a dot predict, and it works perfectly. And then obviously we can store the predictions into a list and compare the percentage error, mean squared error, things like that. Any questions? Yeah? That's a great question. So the way it works is I have observed that when you stack all the models together and you do the hyperparameter tuning, you're actually hyperparameter tuning like the man said, that it increases hugely. But individual models can be trained on separate machines, and then they can be combined. The only thing that you'll need to make sure there is the final layer that you have. I mean, you have to set everything to trainable equals false, and only the concatenation layer has to be trained. So it only learns how to predict combining the individual models and not all the biases and values, I mean, weights and biases from all the entire model. Right? So that's a way to increase distributed computing, but stacking models together and training them also works if the model is simple, if the model is easier. Yeah?
I was thinking if there's an advantage on, because the layer that you had between the concatenation layer and the final, you can make it more complex. You can have two layers or
Yeah.
something more. Is there an advantage to do that? Or
There's no advantage. My experience personally has been that if you add more layers, because you're already concatenating, and then you're taking a layer, there's not much deeper information available to add. I mean, we should be adding layers in the convolutional networks or the individual models, and not after the concatenation, because they can individually predict the price of a house based on the frontal view, let's say, right? But post what it has already achieved, there's not a lot to achieve there. Okay. So we did this, awesome. Other ideas and applications. Before moving to hyperparameter tuning, I just want to give you guys a quick heads up on what are the possibilities of this learning that we just had. So for material sciences, when I work at Polymerize, we started out by understanding that there's a lot of small data sets, right? Just 25 experiments, 30 experiments, or 40 experiments, right? Because experiments take like weeks and they're expensive, so companies cannot afford having like millions of experiments done unless it's a simulation environment. So when we started out, we understood that every, let's say, take for an example, it's an experiment. It has ingredients, let's say different compounds, NaCl, sodium sulfate, etc. Then you have processing conditions. What was the temperature? What was the humidity? What was the, let's say, other factors of what was the rotation, RPM of the motor you used? How fast are you mixing them? What is the speed of adding certain ingredient in the entire compound? And then you have multiple properties. There's properties like heat sensitivity, compression, elongation, all of those individual properties. So you can imagine the width of the data is pretty huge, right? And largely the network, the data is sparse because you're not going to be using every ingredient in every formulation. And there are a lot of cases when ingredients are usually replacements of other. For example, carbon A in one of the experiments, carbon B in another of the experiments. So that creates a lot of sparsity because you have 10 different variations of carbon, and in each formulation you'll only be using one. So if there are 10 experiments that you do, every row has only one value for a particular carbon, and all the other carbons are 0, just to make it a valid network and a valid data set. So the width is huge, but the length is small, right? So what do? We add additional functionalities, and we get some data set by scientific literature, right, and experiential learning. So what do? We find out these chemical compounds. We try to get their entropy, their rotation, their bonds, how many double bonds, how many single bonds, to add that additional valuable information, right, inside the formulation. And then what we started to realize is the structural property of individual chemicals that are going to be part of the formulation add a lot of value, right? Just take for an example, coming from India, we were in standard 10, 11, and 12 here. I think they might call it high school or something else. So when you add two compounds together, not only the compounds, but their direction should also match, because if the directions are different, some other compound might be created. If the direction is reversed, some other compounds are created, right? So the structural property relationship is also a very important factor that we should consider. So there are a lot of libraries that can actually convert. They have the intelligence of converting your chemical name into the chemical structure, right? And then you have these chemical structure images that you can use a CNN with and predict when you actually are combining different formulations, right? So we built this entire platform. We also use a technology called Neo4j, which is a knowledge graph. You can actually store these chemicals in a graphical format. And then we use graph neural networks, which is pretty exciting. It's something that I think everyone should learn about. Once we have that, now we have a network of the experiments that we have, the actual data. Then we also want to know what is the importance of the derived data, the fetching of elongation property, entropy, the bonds, the donors, different data sets that we've derived, okay? And finally, the images. So now we have 3 different neural networks, and they're all going to be contributing to predict the property of the final compound. So this is an interesting application where we can use stack neural networks. The second one is customer retention. You can see there's a feedback text that comes from the customer. There's an audio call as well that the customer and the customer service executive might have had. So that data is also available. We can combine those also, as well as the ratings given by the customers on different products or the purchases that the customers have made in the past. And you can combine all of that data together, build a stack neural network, and predict if the customer is going to stay or not. Any questions?
From your experience, because there are so many models and so much competition going on, is it more prone to overfitting in such
Okay. So what I have done largely is we have an internal tool which does a model validation and checking, right? So there's Dirichlet's conditions that we apply, a lot of mathematical and statistical factors. Like for example, if I pass zeros as a row, right, in the experiment state, if I pass 0 and it's still giving me a property of elongation as 500, right? That does not make sense. So that is a validation factor that we apply. And overfitting, yes, I mean, we look at TensorBoard, all the curves and the different ways to check model properties, but there's a lot of logical validations that we need to do. I mean, there's statistical validations that can be easily printed on a report, but you need to analyze it. But there's a lot of logical validations that need to be done because when a client is using it, he doesn't want to see, something that appears out of nowhere. So robustness is definitely a challenge, yes. Yeah. Yeah? Mm-hmm.
Data types. So for example, there might be a rating or something.
Yeah.
Just have a standard encoding for that.
Yes.
Is that a big problem you found? Is that causing issues?
So we usually go about 5 to 10% of missing data and encoding. I mean, how you handle missing values, right? If you have 50% missing values, it will not make sense. But if you have like 5 or 10%, that works. Because a lot of cases we can generalize. Suppose the customer did not give a rating. So it's a 0 rating, right? I mean, that's how we can generalize. If the customer did not write a text, right? So they didn't even want to give you a feedback. I mean, that's how bad a service they've experienced. So we handle those situations that way. Largely logical, but mathematically we try to use some amount of missing value additions. Anna, yeah, any other questions? Yeah.
You mentioned one of the benefits of stacking is having heterogeneous models. Do you ever, or do you guys ever build stacks with different model families? Not a stack of neural networks, but if you wanted to use like GBM or XGBoost for a good model and
Yeah.
combine that in a stack.
Sure. So the way it works is we can define our own class of making a dot predict, right? I mean, neural networks have a dot predict, as well as the classical machine learning models also have a dot predict. We just need to define a function that can handle that dot predict in the class that we are aggregating different families of networks models.
I'm curious about we'll get to the hyperparameter tuning, same assumptions for the families of models
Yeah.
that you're stacking, what are the kind of problems that you run into or have you run into?
Right. So when the assumptions are not same, the way it works is one particular model performs really bad, the other one performs really well, and they at least balance out the impact such that your accuracy is not absolutely poor, your accuracy is not absolutely high, and the error will be there, obviously, but that error will balance each other. That's why using heterogeneous models works, because if the relationship is not linear and you are using a linear regression model, it's obviously going to give you something not very relevant. But if there is a random forest, if there's another model supporting it, then it might guide towards that situation. And when we do the pass-through equals true or false situation, it's the model also learns for what kind of data do you want to prioritize random forest, for what kind of data you want to prioritize linear regression. And that's what we've seen in explainability as well. Based on a particular data point, you will be seeing that a lot of importance has been given to a particular model. And when that bias occurs, that it's always favoring random forest, that's when we try to make certain kind of changes. Okay. Another interesting application could be marketing. Let's say you are spending a lot of dollars on Facebook, Google, different kinds of channels. Because I worked in the marketing industry, so I have a real-time experience of doing that. But also about the image or the poster or the way you represent the marketing advertisement, that also adds a lot of value. The text that you put in your marketing advertisement, that also adds a value. So there is NLP, convolutional neural network, and deep neural network combined, and that really helps in marketing, because you might be spending $100,000 on marketing with Facebook, but if the text you've written on Facebook is not catchy enough, then that $100,000 will not add as much value as a good catchy title with $50,000 investment, right? That's the conversion ratio aspect, because Facebook has a conversion ratio for converting clients, but the ad itself might have a high quality of conversion or low quality of conversion. I hope that makes sense. Okay, so hyperparameter tuning stacked models. This will involve a lot of code. I am sorry for that. Again, I should have built it better. I actually got my visa on the last day of which I had to book a ticket, so there's no way. Jim here at PyData was really struggling with me. I had around like 30 to 40 emails telling him, yeah, I've applied for the visa. They're not doing this, I'm trying that. So finally it arrived, and glad to be in London. Okay, so for hyperparameter tuning, very, very important, very, very complicated, but easily understood. Let's do this. Ray is the library that we need to work with. All of you will have to install Ray. It does not come installed with Google Colab, just like TensorFlow and other libraries are. Ray is an upcoming distributed training platform. I've used it. It works like magic, to be very honest. Once you've compiled the code, once everything works seamlessly, it can work in a 16-core system, in a 32-core system, and it really saves us a lot of time when building like 500 or 600 models individually. Okay, so data fetch and processing. For the stacked models, we have all the libraries and dependencies we need. Distributed training, I don't want to go into the individual aspects and how they work, but for Ray Tuner, these are all that help you in Bayesian optimization to simulate better parameters for your model. There's concurrency limitation, there's hyperopt search, which is the Bayesian optimization. Hyperband scheduler, how to schedule different models and integrate them with the threads. And tune report callback, which helps Ray understand if the simulation it did is increasing the performance or decreasing the performance of the model. Hyperopt for optimization and the metrics. Okay, not complicating it further with adding more data sets, using the same data set. Train test split. Okay. Now, this is a crucial part where individual model possible hyperparameters can be designed. For a neural network, there's a certain kind of hyperparameters that you would need. For a convolutional network, there's a certain kind of parameters you will need. And with NLP, you will need something else. So based on the experience of machine learning engineers or AI engineers, you can design the hyperparameter space so that the tuning does not take a lot of time. For example, you can see in the first network, I've used Glorot Uniform and HE Normal, which are the kernel initializers. The biases that I've used is ones and Glorot Uniform again. For the second network, I've used Glorot Normal and HE Uniform, right? So I can actually design different hyperparameters, and these designs can also happen at a model level, at a layer level as well. For example, you want to initialize biases and variance weights for every individual layer, you can do that. You can see that in the example. The only thing that you will have to remember is these names should be unique. Otherwise, they'll be used as a duplicate label. It actually works with a named tuple kind of situation, so it cannot have a similar name for multiple aspects of it. I've added dropout. I've also added a batch normalization tuner, which is going to tell me if a batch normalization layer is useful or not. And finally, for the stacked model, finally, I have the learning rate, I have the epochs, and I have the batch size, right? So this is my design space. Okay. Hypertuner. This hypertuner is going to first build network 1. Sequential, dense, activation, bias initializers, kernel initializers, and I've linked them to the search space keys that we originally had. It also has the second layer with the different bias and kernel initializers that you can see, which is again gives us the freedom of designing our networks and each layer of our network. Dropout layer, another dense layer for network 1 because we're going to concatenate it. Network 2, similar procedure followed, kernel initializers, bias initializers for a first layer. Batch normalization, if it is true, there will be a batch normalization layer, otherwise there won't be one. And network 2 will have the final 16 layers, and again, this will not have the final single node because we are going to concatenate it. Stacking the networks together, concatenate network 1 output, network 2 output, we've seen that fundamental idea. Functional API, combined input again, model creation with inputs of network 1.input, network 2.input, and output to be X, which I've just created by using the functional API. Atom as the optimizer, compiling this, model.fit, obviously I have to pass both the training data sets here. I'm fetching the epochs from the space, batch size from the space, and additionally I am adding a callback here. This is very important because if there's no callback of the error, RayTune will not know if it's moving towards the right direction or not. So this entire function that we just created, which is the tuner function, right? This does not return the model. It just has a callback from RayTune integration that will tell us the mean squared error, and RayTune will know in which direction to improve the simulations, right? For example, if it's really performing well with a Glorot uniform initializer, it's going to make sure that it fixes the Glorot uniform and changes other aspects. I did not complicate this further for you because we can actually have dynamic number of layers in each network, and we can also have dynamic nodes in each network doing that search parameter tuning. Right? I mean, the 16 here, they can also be coming from the hyperparameter tuner space, but that's going to take a lot of time to train, and we're going to need GPUs. I've worked with that, so I don't want you guys to go through the pain. Okay, this is another function which is simply a copy and paste, right? There's not a lot of changes except one, which is this function does not have a callback in the compilation because RayTuner no longer needs it. Once RayTuner has got the best set of hyperparameters, we can use those best hyperparameters to train another model, and that will be our final model. It also has the history if you want to integrate it with TensorBoard or if you want to plot the errors for accuracy, that works fine. And we return the history in the model. This function is also done. Finally, the tune DNN. This is where a lot of computational experience comes into play. So you can see this is very important. Resources per trial. Suppose you have a 16-core CPU. So you can actually dynamically have as many instances created, and that many models can be parallelly trained and tuned with RayTune. Number of samples, this is where you add how many models do you want to train. We've done with 1,000, 2,000 models, and you can just, if 2,000 models and 16 processors are used, it does not take a lot of time. And if you add GPUs, boom. The tuneDNN function here that we see takes the best configuration. So the analysis that tune.run gives as a return, that analysis has the best config attribute. The best config attribute is the final hyperparameter tuned space, right? So you will get for each layer, for each aspect, what is the best parameter that you want. Just want to ignore warnings here. And that's it. With tuneDNN and the original space, which has a lot of complications passed, we can see that it trains. This takes some time because there's a lot of initializations that are happening and distributed computing that happens. But you can see that two trials, and this is the dynamically added space where you can see the mean square error keeps on reducing. Right? You can also see the current simulation of parameters, right? From all the parameters that we had passed, there is one value which is chosen from each of those parameters, and the current model that is being run on those parameters. I've just used number of samples too, but ideally it should be more than 50 or 60 models because it increases proportionately to your hyperparameter search space. So for example, if you have 10 variables with 2 variations each, there's 10 to the power 2 combinations that's going to happen. So in that particular case, the number of trials, the number of samples you have to add should be at least 50 or 60 because the Bayesian optimization will not work like a grid search where you have to keep training on all the different combinations, but the Bayesian will definitely optimize towards improving. Okay, so 2 samples trained quickly, and I have this best config, no batch normalization layer, batch size 16, epochs 15, learning rate e power -5, glorate uniform zeros, and the entire dictionary that you guys can see. Again, making a prediction just like we did for stacked networks, works seamlessly by passing a list of individual inputs. Any questions? You can also set the verbose to a larger number, so you'll get a lot more detail about every model that's tuning, how it's improving, how it's not. Okay, working with pre-trained models, that's the last topic for today. So pre-trained models obviously have been trained with the ImageNet dataset, large datasets, huge performances, right? And the only thing we need to do with pre-trained models is to add a line which says set trainable false. Right? So I'll just quickly show you the code for that. I did not bother to make this code completely on my own because there was a good article online. I'm going to add a link to that article pretty soon. Right? So from the Keras applications, we get the DenseNet, we get the ResNet, we use concatenate, all the things that we talked about, the fundamental additions. We create our input shape, use the input layer. The input layer actually helps setting a default input size. So if you want to set a default input size for all the images that you're going to use, you can use the input layer to make sure you first build the network and then worry about how you're going to pass your data through the network. Because in a lot of these cases, the handling of different data sets is the larger problem. The network, as you can see, is fairly simple to build and train and parameter tune. So this is where I'm building the ResNet. I just include one key factor, which is include top is equal to false, which is the final layer of the pre-trained ResNet. I do the same for DenseNet. I use the same set of weights, by the way, so that these models are not trained on different data sets, not learned to detect different kinds of features. And again, include top equals false. Now here, I can actually do customization, right? What do I mean by customization? Suppose you do not want the ResNet to be trained at all, but you still want some amount of training on DenseNet. Or let's say you have a pre-trained model and your own stacked model. Suppose for the housing data set, if I would have used the ResNet or the DenseNet. So the ResNet and DenseNet, I don't want to train on them. I don't want those convolutional networks to be trained because they're pretty well trained. But my numerical DNN or my categorical DNN, I would definitely want to train on that. So I can actually use a pre-trained model, not further train it, except just include the last layer, which is specific to ImageNet, and then concatenate them with the models that I have made. So I can actually use the powers of the ImageNet large data set, as well as use it for my particular use case by concatenation. The idea again is pretty simple. The concatenate layer, functional API of TensorFlow to get access to the combined input. Finally, building a layer of my own. I made it 10 nodes considering the MNIST data set. You can choose the number of nodes in the final layer depending on what your output is. And finally, I create the model and I look at the model summary. You can see ResNet 50 version 2, DenseNet 121. Okay, there's a lot of parameters involved, but I can definitely choose to not train certain parameters, not train certain layers as well, and completely not train a neural network that is a part of it. Okay, so that brings me to the end of my tutorial. If there are any questions, I welcome them. Okay, cool then. Thank you so much. Yeah.
So your experience, you give using hyperopt or using ray to parallelize.
Yeah.
What's your experience like compared, for example, using hyperopt with spark plots?
So honestly, I've not used it with Spark, so I'll not be able to comment. But one of my friends did with PySpark and HyperOpt. And he told me that with AWS and GCP, there's certain kind of complications that happen with PySpark and HyperOpt. But with their latest version of HyperOpt, I think they've fixed it. So it will not create a lot of difference. Raytune is largely beneficial because there's a lot of content available online with respect to model training in a parallel system with Raytune. So TensorBoard integrations and all of those things, they work really well with Raytune. For PySpark, you'll have to write additional code and functions to make sure it matches the idea. Okay. Have a good day. Thanks, everyone.